general, simple introduction. Okay, good. Into quantum computing. So I thought about introducing a very small problem which is related to physics, to correlated electron systems, and presented here. While preparing the slides, it turned out to be a little bit more difficult than expected. So I hope it's interesting for both people who are not from the field and experts. So I hope it's been interesting to all. So first of all, I want to start with some nice pictures. So even though I'm a theorist and I've never seen these machines in real life myself, there are some very nice pictures around, for example, here from IBM. And well, just by looking at them, we don't, of course, learn much from them. So here on the left is just one kind of processor. This is how they look like in action. So in a big duo cooled by liquid nitrogen and so on. So this small thing is the actual chip. Everything around is just controls and machinery on them. So also at RIKEN, we have our own quantum computer. I think it's 64 qubits at the moment. You can see Nakamura-sensei from the RIKEN Center for Quantum Computing, for example, which was recently developed. So these machines are quite big, but basically I want to start very basic. So just the main thing that we have to keep in mind, or basically what distinguishes them from classical to quantum. Classical quantum computer works with, I think most of you know, with two state elements with a single bit, which is 0 or 1. A quantum computer in principle does the same. We have two state qubits, but of course they're a little bit different. We can perform 1-bit operations, 2-bit operations on a classical computer. We can read them out, which state they're in. We can do the same thing on a quantum computer, just with a qubit. But now, of course, the main difference is one is classical, the other one is a quantum mechanical object. So classical bit means it can be either 0 or 1. A quantum bit means it is a superposition between one state and another state, which we also usually label with 0 or 1. It could be maybe spin up and down. It could be some superconducting qubits, many things. But for us, at the moment, basically, a qubit is just a two-level system which you can put in an arbitrary superposition. So the final qubit state can be 0 plus 1 with complex coefficients. The only condition is that it's normalized. So the state can be represented basically by 2 degrees of freedom here on the plot view. Okay, and I was talking about some methods or like some modifications that we can do. So if we have qubits and we assemble them, many of them together, then basically we still need some ways of manipulating them. And the most elementary operations that we have available on these systems is Pauli operators or Pauli gates, so which are called X, Y, and Z. So if we start with a two-level system, let's call it 0, and this is our first basis state. The second one, let's call it 1, and this is our second basis stage. So we have now a two-dimensional system. Then the X gate, which is available, for example, could be lasers and cold atom systems, could be some microwave bulbs for superconducting systems. We don't care so much at the moment how it can be done experimentally, but the operation they do is, on the X gate, is flipping the state. So here you can see the first basis state is mapped to the second. If you apply it, if you apply the X gate to the second basis state, it's flipped back to the original one. And here this is how it's usually represented, a time diagram. So basically we start out with the qubit in some state, we apply the X gate, and then in principle we could check or we could measure, is it now in the up, or is it in 0 or in the 1 state? And the quantum computer will tell us yes or no with a certain probability. Then we have the Y gate. So just very briefly, it's doing essentially the same thing, flipping the state, but with additional phase factors. So here we get the opposite, the second state, but with a complex element in front. For the second basis state, we get minus I in front, but basically then does the same thing. Z gate has a diagonal representation and it just applies minus phase factor to the second basis state. So these are all very simple operations that we have available. And a little bit more general are rotation gates. So many of them are also available on an actual machine. So you can see, for example, some of them, this is more general form. Some of the gates we've seen before can be represented by this one. This, for example, would correspond to something like rotation around the y-axis, where we can parameterize it with a single parameter or angle theta. And this is a little bit more interesting because it doesn't flip, but also puts the qubit in a superposition. So here is already where like the quantumness comes in. If you apply it with a specific angle, we have the superposition actually of first and second basis state. So this is something, of course, we cannot do when it comes to compute. And the next step in quantumness comes in when we want to entangle the qubits, because let's say now we have 2 qubits. So if you have 2 qubits, both can be 0, 1. We have 4 options in total, 4 basis states. Let's label them 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 basis states. Then the most elementary gate that also exists in principle on a classical one is a controlled NOT operation, or in our case, we can also call it controlled X, because it applies an X gate to the second qubit if the first qubit is in the 1 state. So what does it mean? Here, this is first qubit, this is second qubit, left and right. If the first qubit is 0, nothing happens. The state gets mapped onto itself. But the interesting thing happens, if the first qubit is 1, it will flip the second one. So 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. And this is the usual representation as a diagram. Okay, that's basically all we have available for now. So now the question is, can we use it for something practical, for doing some condensed matter physics maybe? So I want to talk about how can we use these simple tools to find the ground state of the hydrogen molecule. So of course we only have these gates available that just introduced. So there is no LAPAC or anything else available on a quantum computer, and there's no diagonalization routine. So we have to find some new ways of reformulating the problem. First, working with only a small number of qubits, which are available today, and also different approaches. Okay, so basically the approach that I want to follow is this one. It's a possible procedure, so maybe in the future there will be better ones. Also in the past there have been other ones. So this is not a unique approach, of course. What we have to do in order to solve the problem of finding the ground state of the hydrogen molecule with a quantum computer is, first, well, we need to define what system we're dealing with, which means what kind of quantum mechanical Hamiltonian we want to look at. This is standard textbooks, quantum mechanics. So if you're not interested or if you're not from the field, you can basically take a short rest for this. Then the second step is, how can we map such Hamiltonian that a quantum computer can understand it? And the last step is, if we have such a representation on a quantum device, can we find somehow a quantum state which has the lowest energy? This is our actual goal. Okay, let's come to the physics part. So the system I want to investigate is essentially here the two-side simplified hydrogen problem. So it's very approximate form, which means we are only interested in the dynamics of the electrons. We keep the cores fixed. They don't enter our Hamiltonian. It's just a static background in the sense that the electrons can be on two sides, on the left atom or on the right atom. And then we have two electrons, which can be either spin up or spin down, which are the internal degrees of freedom. So with this, our basis is essentially we have on the left atom here, there can be an electron with upspin. There could be also an electron with downspin, and the same on the right side. There could be an electron on the right side with up or with downspin. So if an electron is there, I want to put a 1. If an electron is not there, I would like to put a 0, so the number representation. Then the dynamics, what can happen is electrons can transfer between the two different sides. This corresponds basically to the kinetic part of the electrons. There's a finite transition element to go from one side to the other. And there's also potential energy, because electrons are negatively charged, so they repulse each other via the Coulomb interaction. I want to take a simplified form. If they're on the same side, this is energetically unfavorable. But if they're on different sides, they don't feel each other. So it's a very short-range interaction. But for the moment, this simplified model should suffice. So our Hamiltonian has the usual form So hopping between the sites and the repulsion with kinetic and potential term. So maybe many people are familiar with this, but here's a representation in terms of creation and annihilation operators of the Hamiltonian. It's just the reformulating it in terms of a quantum mechanical Hamiltonian, what we've just discussed. So we can move electrons from one side to the other with these annihilation creation operators. If there's no electron, so zero number, I create an electron with this C dagger thing. If there's already an electron, the state gets destroyed. So this can only create an electron, but if there's already something available, it gets destroyed. And the opposite is this C operator. It will annihilate an electron, but if nothing is there, it will annihilate the state. If there's an electron there, oh, I'm sorry, that should be a zero. This is a mistake. So now we can already see some kind of similarity to what we've discussed before, right? So if I now say I want to assign one qubit to the state, for example, for the left atom up spin state. If the qubit is in the zero state, I want to interpret this as there's no electron. If the qubit is in the one state, I want to interpret it as there is an electron with upspin. So now we have a representation. If we can use one qubit for each degree of freedom, so site and spin, we can encode basically the state of the system, where we can encode a quantum state with qubits. So we have 4 qubits, each single one is representative for 1 degree of freedom, either left side or right side, or spin it up and down. And then we are already there at the goal of rewriting the Hamiltonian. So these operations can be put in a neat matrix form. So creating an electron means we go from the first state to the second state. And this can be written in this way. It will destroy an electron if it's already there. So this is why there's zero. The C operator looks like this. So, okay, this is just what I said. It goes from the first to the second state. So this is already something that we have seen before with X, Y, and Z operators. So in principle, we only need to express these matrices, and there's actually not a single unique transformation, but different ones. So if we look at the operators which are available natively on a quantum device, for example, the Pauli gates, we can check that, for example, if we take x minus I times y and divide by 2, we get this C dagger operator. So combining Pauli gates like this has the same action in our quantum mechanical Hamiltonian as creating an electron. Then the same thing for an annihilation operator. We also need an operator which counts electrons, so which is C dagger C, and it can be represented just by the Z gate, for example. These are all the operators which were in our Hamiltonian. So now we have basically a dictionary to map all the terms in the Hamiltonian onto X, Y, and Z gates. So let's do it. And at the end of the day, we obtain something which looks like this. So it's just a string or summation of X, Y's, and Z's. And here I have 4 operators written next to each other because the first one is left up state, the second one is the left down state, third one is right up, and last one is right down. So each of these operators acts for qubits. And now when we have this representation, so we have each term, of course, we need to treat. But for example, if you want to apply one term, we can say that let's start with some qubit state, qubit 0 to 3. If you want to apply the first term, for example, we just put an X, Z, and X gate on the first 3. We don't do anything to this fourth one. And then we have applied this quantum mechanical operation to our quantum state, whatever it might be. Then we can measure it and see in which state it is, can measure the overlap and so on. So without going into the measurement details, now we have a way of, for an arbitrary quantum state, to measure each term in the Hamiltonian, sum them up, and then we have the expectation value of the Hamiltonian, which means the energy. So after this translation of the Hamiltonian, we can measure the energy, and then this allows us, of course, to find the ground state, because now what we can do is we can do a variation procedure, which is also inspired by classical approaches. If we look at well, if we want to find the ground state, we can use that the ground state minimizes the energy. So if we have the Hamiltonian, we calculate the expectation value of the Hamiltonian with that state. The state which has the lowest energy is the ground state. So somehow we need to find this state, and there's many approaches, and we can, for example, come up with the idea of constructing a variational form for that state. And then if we have, for example, a state which depends on some parameters, then we can minimize this, we can optimize these parameters to find the minimal energy. So here, if we have a quantum system with qubits, remember that each qubit encoded the degrees of freedom of the system. So this one was, is there an electron on the left side in the up spin, yes or no? Is there an electron in the down on the left side, yes or no? If we now put some kind of heuristic or arbitrary circuit, so this basically is not unique, it's just something that we can come up with. It's a variational form which just manipulates the state in some way, which allows me to express many different states as best as possible. So here I have some rotation gates, some C0 gates, so it will mix up the quantum state in some unpredictable way. And I have many parameters, here in this case, 8 rotation angles, for example. So it just means the state will be manipulated in some way, it will be entangled in a very complicated way, which I clearly cannot see just by looking at the circuit. The only important thing is that I have some degree of freedom to construct many different quantum states. Probably not all quantum states, but hopefully quite a lot. And hopefully there's a good approximation to the ground state within this space, which I can access with, for example, this small circuit. So if we take this one, it's parameterized by 8 angles. Then let's say we start with some arbitrary angle configuration. We apply the Hamiltonian and measure the energy. And then we can check what is the energy. We update the angles to some different value. Then we check, is the energy lower, yes or no? If yes, we accept this move. If not, we try a different set. So we try out all different kinds of angles until we find one which has the lowest energy, or we converge to something which has the lowest energy. Of course, the more free parameters I have, the better, the more expressive is our ansatz. But of course, then optimization becomes more difficult. So let's keep it at this level. So what we're doing with this is a combined hybrid classical quantum approach, because we do this construction of a wave function and measurement of the Hamiltonian on a quantum device, and it sends us back the energy. Then, for example, with simple Python script, we update the parameters, look if the energy is lower or higher than before, and send the new circuit back to the quantum computer. So it's always a back and forth communication. Update the parameters on our usual machine, letting the quantum computer construct the wave function and measuring the energy. Okay, and well, with this, let's give it a try. So this, of course, is running at the moment on my laptop. That's just as a simulation, but it's doing exactly what I was discussing. So what I'm showing here is there's many functions, but it's a simple Python script using the simulator Qiskit from IBM. And I've just constructed what we discussed. Here is an optimization routine from SciPy. It minimizes a function, and this function is get E0, so get the energy, for a given set of parameters, and it implements simply this gate, this circuit, which I showed before. It measures the energy for that gate for a given set of 8 angles. And then it optimizes it, it reads out the optimized parameters, and then prints the ground state energy and the circuit. So here in this case, of course, the question is, where do we start? Also, this is a very classical problem. We might get stuck at some local minima. Maybe the derivative becomes flat, so we might not get the optimal ground state. These problems also exist in classical approaches. So here, I want to start with, for example, the non-entactic solution, which we can write down right away on paper, for example. So maybe it's a good starting point, but the true solution, in principle, we don't know, of course. So if we run this script, it will now print the different energies and optimize them. So you can see we start at -4, it goes a little bit down, 4, 5, okay. Just looking at the numbers is not so interesting. So let's write them in a file, and then we can have a live view of what happens. So the red point is the optimized energy, and the green line is actually the exact result. So the system is small enough that we can find the exact solution even with pen and paper. And the red line is now the continuous optimization of the circuit angles. So we see we're quite close. Okay, we're not perfectly close to the ground state. Maybe okay. So we're very close and it seems to be converged. So maybe this is maybe not the optimal ground stage, but very close. So now what do we see here? This is the optimized circuit. So it prints the angles that we have found. Then we have the measurement at the end. And here, for example, is a histogram of the states which are obtained. So let me maybe put this on the bottom. Okay, if I pull it a little bit. Okay, it works. So here on the left, which has, so I did 10,000 measurements, and then out of these 10,000 measurements, about 700 times we obtained the 0011 state. So if you look back, the two first are the left side, and the second and the last two are the right side. So this state corresponds to 2 on the right, 2 electrons on the right side. This with 500 counts is 2 electrons on the left side. 1001 is up on the left, right on the down. 0110 is the opposite one. And we see that, okay, the majority is 2 electrons delocalized between the 2 atoms, and then basically the same 2 electrons on the same side. And this is exactly, in principle, what the exact solution looks like. Because of the Coulomb interaction, electrons don't like to sit on the same side. So this probability is suppressed, and the electrons are actually delocalized because they can gain kinetic energy between the 2 atoms in this case. Of course, in principle, these states should be symmetric because of the symmetry of the problem. So these bars should have the same height, and these should have the same height. So this is now the difference, probably, that we have to the true ground state energy, because we didn't reach it exactly. So, like in a classical approach, we could maybe run it again with different starting parameters to finally find a global minimum. But then with this, indeed, we have here now with this circuit, even we don't know exactly how it was obtained because there was this variation procedure. We have encoded the ground state of the hydrogen atom. So now in principle it can be applied to more complicated problems, to larger systems, also to maybe other systems, and so on. So it allows us really to obtain the ground state, for example, of a system. And of course, the hope is that at some point we can treat systems large enough, which are impossible to treat on a classical computer. For now, of course, this was so small, it can be done in milliseconds on a classical one. But yeah, with this, then basically, thank you very much for your attention.
Very nice talk. Thank you very much, Stefan. I really enjoyed it. Are there any questions? Yep.
So basically, the quantum computing part, I think when you measure the state, right?
Yes.
And how is the advantage to measure it on the quantum computer versus, because in this case you have a variation on that, but you can run on a certain basis, and then it's just, you can do the computation, right? It's just a matter of computation, you can compute the energy. Is it most of the case that you can just do complicated matrix computation on a classical computer, and it's kind of fast because the classical computer are fast, versus building a whole quantum computer to actually measure this energy?
Yeah, yes, exactly. So of course, I mean, what I was doing, right, I was solving the problem completely classically, right? But with something in principle, I was simulating a quantum computer. So in principle, this is also a valid variation procedure which I could do on a classical one. Of course, the problem is when you go to larger systems. This is so small that a quantum computer has orders of magnitudes longer runtime than a classical computer because the system is so small. So for this, of course, it doesn't really make sense. It doesn't have an advantage. Then for larger systems, there's very sophisticated variation procedures, for example, to find ground states of large lattice systems or spin systems and so on. And of course, then it becomes a problem. So the biggest advantage, at least for this kind of systems, is in general, the complexity, if you have your classical system, if you write down, for example, Hamiltonian matrix form, this is something which scales exponentially because you have a certain degree of freedom for each atom and then to the power of the number of particles. But here you can see you have 4 degrees of freedom, we need 4 qubits. So, and the Hamiltonian then has 4 gate operations plus something which is linear or polynomial in the number of particles. So in total, the problem that if you implement in a quantum computer is something which more or less scales polynomial. So of course the big question is at what point does it become feasible or advantage to do it? So indeed, it really depends on the system and the size of the system where it actually makes sense to.
You have an example where it's known that it does make sense and n is a feasible number of logical.
So this for now is of course a question which is under current discussion and many people do research on it. Of course, this is something which changes over time because if you develop classical approaches, they become more powerful. Especially like 2019, Google was the first which claimed this quantum supremacy, where they said, okay, we have 64 qubit system, I think, and we did something which a classical computer cannot do, which in this case actually was simply creating a circuit and then sampling the circuit. So doing the same thing that we have done now, we create some circuit and we measure the histogram which comes out in the end. This is what they do, or what they did on a quantum computer. So let's say if I do this for 64 qubits, then of course it becomes really expensive to sample on a classical computer, but a quantum computer just does it in one step. So of course, just simulating a quantum circuit is what a quantum computer can do. And they said, okay, we did 64 atoms. This is out of the reach of a classical computer. But then IBM said, okay, now we have a better algorithm. We can do it in just 2 weeks instead of, I don't know, 100 years or what I said. So of course, if you advance the technology on the classical side, this is a fluctuating boundary where this will happen. So for mathematical or purely circuit systems, I think it might be more clear, but especially physical problems, I think at the moment we don't exactly know when there will be a true advantage.
Yes. Remotely created question. But in this case, the system was simple enough, you know the exact solution. And you can see it converge. But convergence was kind of slow, it looked like. And how do you know you are actually converging to the right number if the system is bigger? And then is there any like risk that it converges to like wrong number somehow? How long does it take? Can you estimate how long it takes to converge to the right number?
I don't think there's a general way of doing that because it really depends on how, but this is also very much a classical problem. Also in variational quantum Monte Carlo approaches, for example, you need to have a good variational ansatz. And if it's more complicated, it takes longer. Maybe we never reach the ground state because we get stuck in local minima. In this approach, we have exactly the same problems. So if the system becomes larger and larger, also there are works purely on how, for example, this variation procedure behaves with larger systems. And from, if I remember correctly, it seems even to be less well conditioned than in a classical case. So this seems to have very large plateaus with no derivative. So you might get stuck quite easily, actually. So that maybe this approach is not scalable to very large systems. Of course, there are other approaches to, for example, calculate approximately eigenvalues of a Hamiltonian, but at least for now, this is the most popular and successful approach. So the final answer is, of course, we don't know. two ground states.
So does it work for a highly degenerate ground state? You have deterrence, that's the reason it's getting slower to converge.
Yes, of course, if you have degenerate ground states, then exactly we have also the same problem in classical approaches. Then in principle, you might get stuck in only one solution. In principle, this approach should be, if it's ergodic, it should be able to sample all of them. And then we measure the correct energy. So yes, indeed, it's a problem. So I think in practical cases, it would get stuck in one of the degenerate ground states. So this cannot distinguish properly between degenerate ground states.
So can you like break up degeneracy like do? It's good.
This would, yeah, this indeed would be possible. That's true. So here, in this case, actually, there's only one non-degenerate ground state.
Question about not this one, but the device. I mean, 2 days ago, how about MIT group announced a Nature paper announced that they could do I think 48 logical qubit instead of just
yes. So I didn't have time to go through it completely, but there was this announcement of a system with more than 200 qubits based on trapped atoms, which have usually quite a good fidelity compared to superconducting qubits. And so what we did here is we did a physical qubit approach. So each qubit encodes 1 degree of freedom. On a classical computer, also, this is usually not done if we have error correction, for example. So we use, for example, more than 3 bits to encode 1 qubit, 3 bits to encode 1 bit for error correction purposes. So now it seems that one group has managed to do a sophisticated error-controlled qubit quantum device, implementing some error-correcting code, and it seems that they have something which can be practically used, because at least from what I know, even implementing error-correcting codes, the problem is each qubit in each entanglement operation is so noisy that it eats up the advantage of entangling more than 1 qubit together, so that there's no advantage of trying error-correcting codes because the full code is more noisy than just a single one. But it seems maybe that this group has managed to achieve a workable quantum error-corrected qubit.
So in this problem, the 2 qubits were the same. Like, yeah, the physics for each one was the same. If you went to a system where, say, the energy in one state was, like, say it was 1 hydrogen, 1 helium. How well does the serve algorithm work if you don't have like a symmetry?
I mean, in principle, this algorithm is very general. It doesn't care what the Hamiltonian is. The only thing is then I would adjust the Hamiltonian. So basically here you can see that I have no difference. So you can put an on-site energy to the different atoms in order to simulate, for example, different type of atom. So then this, at least this variation approach, in principle is independent of the Hamiltonian. If your ansatz is expressive enough, that the ground state is approximately an element of the reachable states, then it should be accessible.
Well, as far as I remember, for this Google claim, basically there was strong skepticism that it is even a quantum computer. So as far as I remember, the problem they solved, this was a really highly treated code, very, very specified one single problem. So I'm personally very skeptic that they're a quantum computer. So what do you think, quantum superiority or whatever this is? So has there been any proof so far that they really achieved this? And B, what do you think, when will you achieve this?
When it will be achieved, I think I wouldn't dare to say, because this is quite uncertain, but because of both developments on the quantum mechanics and on the classical side. So this is, for example, why IBM was harshly criticizing the Google claim, because Google claimed that the problem they did should not be able on a classic computer within hundreds of years, I think. But then IBM said, okay, we have an implementation which actually can do it 2 weeks, which of course then 2 weeks compared to 100 seconds on a quantum computer, is this really an advantage? Pumping hundreds of millions into a system which can do just 2 weeks compared to 100 seconds. So, I mean, quantum advantage for these high specific problems basically will be reached very soon, or is basically right at the border right now, I would say. The question is, of course, whether we have practical quantum advantage. If we just have a quantum computer which can sample any arbitrary circuit better than a classical one, this doesn't help us if the circuit doesn't correspond to some mathematical or physical problem. So the question is whether for a truly application there's advantage. And this seems to be much harder. And at least from what I've seen, there are papers where people claim, okay, maybe this condensed matter problem is suitable. We only need 100 atoms in order to reach, or 100 qubits in order to reach supremacy. Then there are other papers which actually said, okay, it's something, actually the state preparation is more complicated than assumed, so it will be much harder to reach advantage. So it's very fluid, I would say. I think it's too hard to say when it will happen. It could be, if someone comes up with a very clever quantum algorithm, it could be much earlier. If something turns out to be, if people come up with a very good classical algorithm, it could also be much later. But it seems promising, I would say.
If you have more a classical system, I imagine you want to solve lots of Poissons. Is there a systematic way to map it to
you mean just a purely mathematical problem, for example? Yes, I think there are methods of mapping, for example, differential equations on being able to solve it with quantum computers. But I haven't really looked into it. I've seen some works on it. So I think there's a way to do it, but I don't know the details, unfortunately.
There's a matrix, and you choose a basis, and
oh yeah, if you can find some matrix representation,
may not be the best way, but that's special work.
Yeah, that's true. If you have some kind of matrix representation, you can apply it principle.
So the number of degrees of freedom is what you are representing the matrix of finite size? Yeah, okay.
So my understanding is that for the Glossop-Poisson equation, the reason for Glossop-Poisson example, the reason it's difficult on quantum computers is that the density that goes on equation is the wave function squared. So you no longer have a linear operator to do the computation. And I guess there's ways around this, but somehow that's what makes it harder. But it's also better.
There is no wave function. I still, so it's just I mean, do you have any other variational answer? So why did you choose this one? Well, I mean, what's the basic logic of this choice?
Yeah, so this is something I think which emerged over time. So basically, it's really kind of heuristic approach. We want something. So of course, each single qubit can be in something between 0 or 1. So we need something which does a superposition between two, which is a rotation. But then we don't have any quantumness like multiple Slater determinants, for example. This is what the C0 is doing because it entangles the qubits. So at least this is the most basic way of creating superposition of states, and then it's essentially a sum of Slater determinants by using the C0s. So of course, no one tells me that this 0 and 1 C0 should be here instead of here. So it's just basically there's some arbitrariness in the methods because this is something which has crystallized out over time.
Okay, thank you. Are there any questions from the people on Zoom? Okay, I have a quick question actually, which is just in this example, you just used a very crappy minimization method to try and, explore the states, which is definitely not the way to go. But I guess that's my question. My question is it normally how people do it, or is it just for the purpose of a demonstration? Or do people get a lot more sophisticated?
I mean, what do you mean by more sophisticated? I mean, in the general idea of doing this variation procedure to find a ground state like this, with this kind of ansatz, is indeed what people have been using or are at the moment also still using. Of course, there are alternative approaches developed. This is not the only one to find a ground state. So actually, already before that, there were many ways of estimating, for example, the eigenvalue or ground state energies. But so far, this turned out to be very practical compared to other approaches.
But in this case, you're not looking for a value, you're looking for a distribution of values, right? And so in that case, this minimization method that's being used, so I thought you were just doing it for the purpose of demonstration, but if that's actually what people are using, then we probably should talk. Because I don't know anything about quantum computing, but I know about parameter estimation, and this is not a good way to do this.
Okay, for sure. I think it would be very interesting to talk, but this is also what people are using for much larger systems, for example. So if you can come up with a very good approach, then
yeah, we should definitely talk then. I did not realize that's what people were doing. That is not a good way to do this.
Okay, let's discuss. Thanks.
Okay, sounds good. Thank you. Are there any further questions from anyone else? All right. Well, thank you for the very engaging talk today. Let's take our speaker one more time. And before I wrap this up, are there any last announcements before we close the coffee meeting? Wonderful. All right. Well, you guys have a nice rest of your day and enjoy the conversation in the coffee meeting. And Stefan, I'll catch up with you next week.
Okay, great. Thank you.
Thanks, everyone. Have a good weekend. Bye-bye.